Why don't spacecraft freeze in space? Heat, temperature, and the physics of the vacuum. Anyone who has ever been curious about space has probably asked this question at least once. If space is so cold, why don't spacecraft freeze? At first glance, the question seems simple, but behind it lies a surprisingly deep subject involving physics, engineering, thermodynamics, and even how we understand the universe itself. What's more, finding a truly detailed and clear explanation of this topic online isn't easy. So in this video, we'll build the answer from the ground up, step by step. To understand this properly, we must first clarify two concepts that are often confused: heat and temperature. Heat versus temperature. Heat is a form of energy. Whenever energy flows from one object to another due to a difference in temperature, we call that energy heat. In simple terms, a hotter object transfers energy to a colder one. This process is known as heat transfer. Temperature, on the other hand, is a measure of the average kinetic energy of the atoms inside a substance. The faster these atoms vibrate, the higher the temperature. For example, boiling water has a high temperature because its molecules move very rapidly. But that doesn't necessarily mean it contains a large amount of heat energy. Heat depends on how much energy can actually be transferred to another object. In short, temperature tells us how hot something is. Heat describes the flow of energy between objects. Confusing these two concepts makes it much harder to understand how temperature behaves in space. Units of measurement. Heat is measured in joules, or sometimes calories. 1 calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. This is where the calories we talk about in daily life come from. They're simply units of energy. Temperature, however, is measured in Kelvin, Celsius, or Fahrenheit. In scientific work, Kelvin is almost always used. That's because 0 Kelvin represents absolute zero, the theoretical point where all molecular motion stops. Kelvin uses the same scale as Celsius, but with a different starting point. 0 degrees Celsius equals 273.15 Kelvin. Kelvin never has negative values. This makes it ideal for scientific calculations, especially in physics and engineering. Celsius is what we use in everyday life. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. Fahrenheit, used mostly in the United States, places water's freezing point at 32 degrees Fahrenheit and boiling point at 212 degrees Fahrenheit. While it allows finer gradations, it's rarely used in scientific contexts. Frankly, systems like feet, miles, and Fahrenheit are a mess. That's why engineers and scientists rely on the metric system and Kelvin. And yes, space engineers always calculate in Kelvin. How does heat transfer? Now we arrive at the most important part. Heat can be transferred in 3 ways: conduction, convection, and radiation. On Earth, most heat transfer happens through conduction and convection because we're surrounded by air, liquids, and solid materials. Heat is essentially energy passed from one atom to another. Atoms vibrate, and that vibrational energy spreads to neighboring atoms. For example, when you stand near a campfire, atoms in the fire vibrate intensely. That energy transfers to nearby air molecules. Warm air moves towards you. Those molecules transfer energy to your skin, and since we are made of atoms, we feel that energy as heat. But space is empty, so how can it be cold? Here's where things get confusing for many people. If temperature is about atomic motion, how can space, which is nearly empty, have a temperature of minus 270 degrees Celsius? The key point is this: space itself is not cold in the way we experience cold on Earth. Cold implies something actively absorbing energy, but space has no medium, no air, no atoms to carry heat away. If you placed a thermometer in deep space, it wouldn't instantly freeze. There's nothing there to steal its heat. The value of minus 270 degrees Celsius comes from the cosmic microwave background, the faint glow of low-energy photons left over from the Big Bang. This radiation corresponds to a temperature of about 2.7 Kelvin. So space isn't cold because it actively removes heat. It's cold because it contains very little energy. How does the sun heat Earth through empty space? The answer lies in photons. Inside the sun's core, hydrogen atoms fuse into helium, eliminating enormous amounts of energy. This energy escapes the sun as photons, particles of light. Photons can travel through empty space. They don't need air or matter. After leaving the sun, these photons reach Earth in about 8 minutes and 20 seconds. When they strike Earth's surface, they transfer their energy to atoms, increasing their motion. That's why sunlight feels warm on your skin. But here's the crucial distinction. Photons carry energy, but they do not heat empty space itself. They only transfer energy when they hit matter. What happens to a human in space? Movies often show astronauts freezing instantly. That's wrong. In space, your body can only lose heat through radiation, which is a slow process. You wouldn't freeze immediately. It could take hours to lose enough heat to freeze. The real danger is pressure. With no atmospheric pressure, gases in your blood expand. Air escapes your lungs. You lose consciousness within seconds. You would suffocate long before freezing. Cooling would continue gradually as your body radiates energy away as photons. So why don't spacecraft freeze? Let's look at the James Webb Telescope. It orbits about 1.5 million kilometers from Earth at the Lagrange 2 point, mostly shielded from direct sunlight. James Webb is divided into two regions, a hot side and a cold side. The sun-facing side contains electronics, solar panels, and communication systems. These components operate at around 27 degrees Celsius. How is that possible? Because Webb maintains a precise energy balance. Its reflective surfaces bounce most incoming solar radiation back into space. Very little energy is absorbed. What is absorbed is carefully radiated away, keeping temperatures stable. The telescope's most critical feature is its 5-layer sun shield, which blocks 99.999% of the sun's heat. The cold side. Behind the sun shield lies the cold side, where the mirrors and scientific instruments are located. Temperatures there drop to minus 233 degrees Celsius. This extreme cold is essential. The telescope detects faint infrared signals, and if the instruments were warmer, their own heat would overwhelm the data. Doesn't everything freeze at minus 233 degrees Celsius? No. Freezing refers to liquids, especially water, turning into solids. Spacecraft aren't made of water. They're made from metals like titanium, beryllium, and aluminum alloys. These materials remain structurally stable at such temperatures. For example, titanium melts at 1660 degrees Celsius. Beryllium melts at 1287 degrees Celsius. At minus 233 degrees Celsius, these metals simply vibrate less. They do not freeze in a destructive sense. Final thoughts. Freezing and cooling are not the same thing. Space isn't deadly because it's cold. It's deadly because it lacks pressure. And spacecraft survive not by defying physics, but by using it perfectly. Unfortunately, misinformation spreads easily online. Claims like space is absolute zero, so nothing can survive, ignore basic physics. My goal here wasn't to overwhelm you with equations or technical jargon, but to explain heat, temperature, and energy balance in space clearly and honestly. If you enjoyed this video, consider leaving a like and subscribing. I regularly create documentaries about galaxies, stars, planets, and space science. See you in the next one. Take care.